Okay. So last week I threatened the class with not giving them a lecture because there wasn't a quorum, right? And now we have even less. So now I have to figure out what to do with less of a quorum than I had last week. I need my water.
Just do your thing.
Do my thing. Yeah. I'll do something, and I'm going to do something. Okay, look. This is the thing. So I've been really studying up on this stuff because it's really interesting. And the more that I study about it, the less I know, which is always good. And so I thought I had a clue as to the Big Bang. And then I found some stuff which was really interesting to say, oh, yes, but. So that was what the lecture was going to be, and it still might be. But then I was confronted with even one more epiphany, which is that I realized that up to this point, I myself was really not buying into some of the stories that they tell about the Big Bang, because I'm a skeptic, and without knowing enough about the Big Bang, I was kind of like basically doubting whatever I was seeing. I want to make sure that thing is recorded. Hold on. Are you recording? Yeah, it's recording. Yeah, so I basically doubted a lot of the things that I knew about the Big Bang, and now, if you will, I'm doubting less. So I'm becoming more and more convinced that something as incredibly weird and strange as the Big Bang, which seems a story that couldn't really be true, is in fact really true. And the part that I was going to tell you last week, which is the part that makes, the Big Bang is true, but here's this controversy. Now the lecture is more like, let me tell you about the Big Bang, and incidentally, there's this controversy. So the Big Bang is a big deal, and I didn't get it. So let me tell you what I didn't get. So that's the subject of today's lecture, my confusion about the Big Bang. And then we'll get into the part where I was going to talk about last week, but didn't. So my confusion about the Big Bang is it's really hard to buy into the idea that the universe, the universe began sort of in a singularity. It just happens, and then the universe just blew into everything, and so everything that's out there is part of the thing that just began in one little instant, in 1 millisecond, nanosecond. Those are not the right partitions of time. Really itty bitty, smally bit of time that the universe began, and then everything came out of that. That's the Big Bang in a nutshell. Everything came from nothing. Everything was compressed into the most ridiculously compressed thing ever. And then things got bigger and bigger and bigger until other things happened that we're more familiar with. And on the way from what's familiar now to what was unfamiliar then, all sorts of really strange things happened in a very short amount of time. And
that's how babies start.
Not that way. No, babies don't start that way.
There are things that there is one theory.
Yes.
That universes are like bubble wraps; they come in and out.
Okay, so the business about bubble wrap universe. You know, that fact that maybe the universe is just one of multi-universes. See, that's one of the things that I can't wrap my head around. See, there are some crazy things, string theory, multi-universes. That's two. Things that really aren't really true, but people seem to believe it. It's not that they're not true. It's just that there's no proof. And so me as a skeptic would find it hard to buy into those. But the Big Bang, for God's sakes, the Big Bang, I should believe in the Big Bang. I'm a scientist, or at least I pretend to be. And I'm rebooting my machine at the same time that I'm trying to tell you this stuff. Again, things like multi-universes, bubble universes, and stuff like that. That's really hard to believe. But why? But Elaine, you like to go there. But I think the Big Bang is hard enough to believe. Why aren't you stuck at the Big Bang? Why do you believe in the Big Bang and want to go for bubble universes?
Because I went to the science fair, and all the scientists there believed in multi-universes.
They all believe, but there's no evidence for multi-universes. They just like it.
But
They like it.
there's no evidence back when Galileo got started, and
Right. No, so the thing about the Big Bang is the more we learn about it, the more it confirms what we know. Whereas the thing about multi-universes is the more we learn about it, the more we haven't learned anything about it. It's just a good idea that essentially eliminates the need to talk about God. Okay, that's what the multi-universe is. If you accept the anthropic principle that we're not in the center of the universe, that the world was not created for our benefit, that it doesn't revolve around us, and that we're just like every place else in the universe and we're not special, then you're confronted with the fact that the universe seems to have been personally constructed for our benefit. It's so well done. If you changed it in so many little ways, the universe as we know it would disappear, not exist, and we wouldn't be around to be talking about it. The very fact that we're around talking about the universe means that somehow or other it's special. That bothers people a lot. So they say, wait a second, let's not be special. How about if we throw out the idea that there's an infinite number of universes and we just happen to live in the one that works? As soon as you do that, you eliminate God and you eliminate special, and you're done. But there's no actual evidence for it. I happen to like multi-universes. I'm a fan. I don't believe in God. But but if you can believe in God, and the Big Bang can work for you. The only time you go into atheism is if you say, well, let's have a multi-universe so we don't need God, because God could have created the Big Bang, right? He decided to make a really special place for us all to live in, and went poof. And not only that, but it's even better. It begins with, let there be light. And there was light. Turns out the light didn't happen for 400,000 years, according to the actual theory, but that's just a minor point. Why is that? Okay, so let's start with the light didn't begin for 400,000 years, part of the lecture. Okay, why would that be? Why, if there was a Big Bang, why didn't the light start for 400,000 years? That seems insane, right? Because it's obviously the world was really compressed, things were really, really tight, and it was really, really hot. So how could it not be that there was light? So the answer to that is, well, the problem was there was light, but you couldn't see any. First of all, if you were there, you would have been, a toasted marshmallow, so you wouldn't be around to be observing. But in the theoretical instance that you had an observer that could be capable of registering photons in some way, then yeah, there was light. Like right now, I'm a person that's capable of registering photons. I am a measuring device, and the photons that I'm measuring are from the 1, 2, 3, 4, 5, 6, 7, 8, 9, now 10 people in the room, okay? And I can see those photons coming from all of you, okay? What happens if the room was filled with fog, okay? Fog, so that I couldn't see you at all? Then you could say, well, there's light, but it's just bright. I can't see anything. So whether or not it's dark or bright doesn't make a difference. I can't see nada, right? That's the way the universe was at the 400,000 year mark. Invisible, although there were things in front of your face. If you had a hand and you could hold it in front of your face, you couldn't see your hand, right? So is it meaningful to say there was light? Yeah, there was schmutz in front of your hand that you couldn't see that made your hand invisible. So, okay. So yes, that schmutz was light rays, but the light rays didn't travel any distance whatsoever before it got intercepted by something else that stopped the light ray from getting to you. And what was that something else? Well, that something else that got between you and it was the rest of the universe. The universe is made up of things that go bump in the night, mostly, and then us. Okay, so us is, as we have been told, is 5% of everything, and then there's the rest of the universe is dark matter and dark energy, which you've heard about. But 5% of that is us, which is, of course, one of those crazy facts which is hard to get your head around, and the fact that the Big Bang Theory happens to like that explanation and likes it very well, and keeps, if you will, reiterating those particular facts, which we'll get around to. But fact is that aside from those 95% of things that we really want to ignore here, the 5% is us. The 5% is the atoms, the protons, the neutrons, the electrons that make us up, okay? And those things were the things that stopped us from being able to see things, because the atoms were right in our face, and the atoms, but that doesn't do it for you. If you really want to mess with light getting from here to there, you need to put something in between here and there that will scatter the light so it doesn't go straight. Because if it could go straight, then I could see you. So the thing you do to scatter the light is you create an atom, proton, and an electron. And what you do is you have those two things separated so they're not part of an atom, because they haven't, in fact, atoms have not yet been invented in this earlier part of time before this little era that I'm talking about, which by the way is called it's called the end of the darkness. It's the first light, they call it. These atoms were ionized atoms, were interfering with the light, and the light was scattering off the atoms. So they went this way and that way and this way and that. Not the atoms, the protons, the electrons. The light was being scattered by these ionized gases, and they couldn't go in a straight line, so they never got to you. Let's do a timeline of the universe, if I can do that. And that seems weird that you could do a timeline of the universe. But in fact, when the universe was young, it was a time before the universe had gotten any good ideas. So right now, the universe is filled with good ideas. I think there's at least 10 people in this room with good ideas. Okay, so everybody in this room not only has good ideas, but is a good idea. In fact, the chairs are good ideas, the room is a good idea, the building in which we live in is a good idea. But by that I mean, everything is different from everything else. Okay? But in the beginning of the universe, there was no everything is different, because all these things separated to become chairs and you. There was a while before the chairs and you were all part of the same cosmic goo, and it eventually took 4.5 billion years for somebody to invent chairs and you. But in the past, all they had was the goo, and the goo was simply made up of protons, electrons, and neutrons, and some other stuff which we'll talk about. So the universe was uniform, and because it was uniform, and this is really the good news, is we can actually talk about it as if we know something. If I was trying to talk about you guys in the room as if I knew something, I'd get it wrong 10 times, 11 times, 12 times, because what do I know about you? You're so different from each other. But the goo is all the same, it's uniform. So we can talk about the stuff at the beginning of the universe as if we know something. It's not like, well, if you knew a little bit more, you'd be able to distinguish the X from Y. No, it's the universe is uniform. We can examine what was going on in the early part of the universe. So let's say, oh, not that. Is my screen responding? Yeah. So this is a picture of the universe from the beginning to now. All space, all time. It's beautifully done. It's very simple. Okay. Here's the Big Bang. Okay. Then things got bigger, and then after that they still got bigger, but not so much, and things became more defined, if you will, more individualized. And here, back in the beginning, things were more like the same. And this was sort of at the very beginning, and we'll talk about all these stages. But the part that I was talking about was a part right of, where is it? Yeah, afterglow light pattern, 375,000 years. 375,000 years was the time after the Big Bang. Big Bang began at 0, right? The Big Bang began at t equals 0. I love that. If you're a physicist and you go to physicist school, okay, one of the things that they give you in physicist school is equations involving time. And equations involving time, there's always a t equals 0, which means the beginning of whatever you're talking about. But in the case of the Big Bang, t equals 0 is like the beginning of everything. Okay, physicists can have all little t equals 0. Let me roll this ball down this track, and we'll start at t equals 0, and that's fun for the physicists. But this is the real t equals 0. There's no other t equals 0. This is the first one, and it's 13.77 or 13.8 billion years ago. There was a t equals 0, the beginning of everything. And after that t equals 0, 375,000 years later, and you got to get that that's a ridiculously precise number, okay? I mean, it's really, you know that number? Yes, they know that number. Now, it's true that this number does change from time, depending on who you're talking to. Sometimes it's 400,000, sometimes it is 500,000. This number tends to get more and more precise over time, but nevertheless, it's a number that they don't dispute as being the number around here. And it's called the time that that light was first able to make it past those electrons and those protons and those neutrons. The first time the light was able to get past that, so you could see something. First time that you could ever see something. And then that light, that first light, went on forever. So some of that first light, I'm pretending I'm a radio telescope, some of that first light is passing by my radio telescope ear right now, right this very second. Some of that first light from 375,000 years ago is passing by me right now. It's the sound of the Big Bang, although it's not sound, it's light. But that light that first got a chance to escape from the bubble that was the Big Bang is passing by us to this very day. That's, I could go home right now. I think that's enough. Okay? I mean, really, can you buy that? Because it took me decades to buy that, what I just told you. I now buy it, but surely you have 1,000 questions. That seems so wrong, right? The Big Bang the sound, or if you will, the light from the Big Bang is passing by us at this very second. There's nobody in the room who says, that doesn't make sense. Come on, somebody say that.
Yeah, well, what came up with the first idea of that kind of thing? Was there mathematical formulas?
No, it was an accident.
No. Which person just
There's
communicated such an idea?
There were a number of people who had the idea. Okay, a number of people who had
What
the
did they base that
on the idea that there was a Big Bang. Somebody said it goes like this: there was a Big Bang. We think there was a Big Bang. Here's the evidence that we think there was 100 years ago. 100 years ago. 100 years ago, somebody said, we think there was a Big Bang because it explains a lot of the stuff that we see. Well, if it was a Big Bang, then it was very, very hot. But the universe got very, very big after it. And the universe got very big, so the hotness got distributed over space. So hotness now should have been cooled off. So the universe should have cooled off. So if the universe cooled off, then we should be able to measure the temperature of the universe. So let's do that. So somebody said, let's do that. And they designed an instrument to measure that. So this is New Jersey, in 1960s, something like that. Somebody said, let's design the instrument to do that. I'll take this device here, which is a radiometer or some sort of device, which I'm very expert at building. I'm the world's expert at building this device. I'm going to build it. I'm going to add a telescope to it, and I'm going to look at the sky, and I'm going to find the aftermath of the Big Bang. Meanwhile, 20 miles away, there was two guys, who happened to have that guy's radiometer, the previous version, hooked up to a radio telescope, because it was one of the first radio telescopes, and they had it pointed at the sky, and they were going to look to see what the sky had to offer, a little bit of this. But the problem was that every time they turned on the instrument, they got a buzz. They got a buzz. And they couldn't figure out what it was. They went and tried to clean the instrument. Finally, they went to this guy. They said, there's something wrong with your radiometer thing, because it keeps buzzing. And he said, no, it's not buzzing. That's the sound of the universe birth. And these guys got the Nobel Prize. Not the guys who built the instrument, who were going to do it, who told them what it was they were listening to. These guys got the Nobel Prize.
So you have to disprove that.
What? No. If you guys, watch the Big Bang Theory on television, they're actually imitating part of this. They have the main characters have discovered something that nobody's ever discovered before, and now they want the Nobel Prize for it. But two other guys who didn't have a clue what they were doing happened to be pointing their telescope in the right place, doing the right thing at the right time, and got the discovery which proved the theory. And these guys want the Nobel Prize. And so you have the theoreticians wanting it, and the experimentalists wanting it. And the truth in the real world is the experimentalists got the Nobel Prize. I think that is the worst award of the Nobel Prize I've ever heard of in my life. Somebody was raising their hand, yes.
You say that the Big Bang happened, this really compressed thing in space,
Right.
and that it expanded into space, okay? So where did this space come from, and where did the time come? That was already there.
Yeah. So those are good questions. Okay, you're not going to like the answers. Okay, I'm going to just give you the stock answers. Okay, and then for homework you can go home and Google what is he talking about, because how could it possibly be true? The one that's easiest to believe is time began at the Big Bang. That there was no time before the Big Bang. The time and space were created at the same time in the Big Bang. Okay, so that one was a little easier to believe. Those of us who want to believe in multiverses, okay, which would also go with the idea that time is infinite, has been going on long before the Big Bang, and that these universes keep popping up in the space of time and space, so that in fact, time didn't begin with the Big Bang, well, then you can join the crew in the corner of the room who believes in multi-universes, and then you don't really need time to begin the Big Bang. The rest of us who think that, well, there's only evidence for the Big Bang and nothing else, then we go, well, okay, time began at the Big Bang. It's not satisfying.
So is this universe, the one universe, infinite?
Okay. I'll answer your second question before I answer your third question. The second question is, what is it expanding into? Okay? What is space expanding into? And you're not going to like the answer to this one, because the answer to this one is space is being created. It's not expanding into anything. Okay? And then you're going to really not like the third one, which is, and space is infinite. I'm just quoting. I'm quoting things that people much more knowledgeable than myself really do say, and 9 out of 10 scientists believe that. And that means leaves one scientist who maybe doesn't. But as you know, in the old days, there were 4 out of 5 dentists who recommended sugarless gum for their patients who chew gum, leaving one dentist who recommended sugar gum for their patients who chewed gum. That dentist turned out to be wrong, although I don't know where they found him. But nevertheless, there are some honest-to-goodness scientists who do believe that maybe space isn't infinite. 1 out of 10 scientists say maybe it's not infinite. The thing is, if it's not infinite, you have a lot more explaining to do. It's easier because when you can just wave your hand and say it's infinite. As soon as you say it's not infinite, then you get into questions like, well, what's beyond the end?
The other universe.
Well, yeah, right. And where do you get these multi-universes from? Right. If the universe is infinite, how do you get an infinite number of infinite universes? Please explain that to me. So that is what multiverses are: an infinite number of infinite universes. Okay. So that's where I stop. That's why I'll just repeat the dogma, and I'll be one of the 4 or 5 dentists who recommend sugarless gum for their patients without necessarily having a clue as to whether or not it's true. I just joined the multitude. Where was I? Oh yes, that. So right there. Okay, you see this? See this? This right here. That is the 4. Let's call it 400,000. 400,000 year mark. Okay. And you see that looks like there's a picture there. So actually, we have a snapshot of that. Because if there is radiation coming from here, from the Big Bang, and radiation coming from here, from the Big Bang, well then surely I should be able to point my camera at it and take a picture of what it looks like. Because radiation is light is coming at us. Let me get out my trusty camera and take a picture of it, and I'll take it and show it to you folks. Sure. I made it sound as if that's absurd, but of course it's not absurd. In fact, it's the next picture I'm going to show you. The first time we took the picture of the universe in 1992, this is what it looked like. This represents a 360-degree view. Okay, whereas if you take a globe and you spread it out, you can get that sort of projection. So that's everything. Okay.
Who took the picture?
The name of the satellite that took the picture was Cosmic something background something. Okay. The name of the satellite was Kobe, and it took that picture in 1992, and it got people pretty excited. And then, so they sent out another satellite, and they took this picture. See, same picture, but more detailed in 2003. And this drove them wild because now they could explain this. This they could explain, but this gave them the data they needed to say, let's test our theory against that. That's the universe. Let's see if our theory explains the universe. And the answer was it did. Then, when they finally took this picture of the universe, and it turned out to be a better picture, this picture is the picture that is causing all the controversy, because this picture is not this picture plus one other fact is a controversy because this one is too detailed to ignore. This one tells you so much stuff about the universe, what it looked like at 400,000 years old. There was stuff going on. I told you that the universe was the same everywhere. That this piece of gook was the same as this piece of gook. And that was true. But this picture shows 1 part in a million difference. It's the 6th decimal place that we're looking at here. The thing is the same. The 6th decimal place is different. So there's differences. And the differences and the story is in the differences. So this is a snapshot of the Big Bang, when the Big Bang first opened its robes and said, "Here I am. This is the universe. All right, I did it. Okay, this is me.
You're under arrest.
You're under arrest." Right.
How can they go back enough? I can't conceive of being able to make a picture of the universe at 400,000 years old.
Well, first of all, the number 400,000 years old is a conversation that does not necessarily appear in this picture. They figured that out from other stories that I haven't really told you, although I've implied it. I said there was a time when the universe cleared up so you could see through it. Okay, and so they could figure out what that time was, and I could show you how they figured it out, or at least the timeline. So they go, oh yes, now. Okay, so that's how they figured it out. What it looked like in the first place is well, they're not using a camera. You point a camera at something, light rays come in, they expose the film, or charge coupled device, the what do you call the thing? Anyway, the thing that the light hits upon these days, inside the camera. What's the sensor? Thank you. Okay, this is we lose words one at a time when you get old, so that's one. So it impinges it upon the sensor, and the sensor, if you got a nice lens, you get a picture and you're done. Okay, but if you don't have a nice lens, what you do is you take a straw, soda straw, make a long soda straw. You look through the soda straw, and you go, "That's a 12. That's an 11. That's a 14." Okay, so now you have data from every point in the sky taken through a soda straw. That soda straw is the radio telescope, and what it's doing is it's pointing very narrowly at one spot, and then it moves and it looks at another spot and very narrowly looks at that, and you add up all the data from all the spots and you get a picture. Just one itty bit, one pixel at a time, rather than, as your camera takes it, all the pixels all at once. Yes? Did you have a question? Yes.
So, how can we say this is the whole universe?
Because they point it in all directions.
Camera
They point it in
a
all directions.
circle?
And the camera turns out to not be on the Earth. It turns out, the first camera was on Earth. That's probably where you saw that picture. The first poor picture was taken from that radio telescope that gave people the Nobel Prize. Okay, but then they launched satellites to do the same thing, and so they got better pictures.
So they went 360 degrees.
Right.
Every direction.
Every direction, looking around the entire sky. They looked at the entire sky. They did it for years, 4 years worth of data. Here's your 4 years worth of data. Thank you very much. $100 million, please. Next guy came up. I'll take $500 million and I'll do the sky for you. They did the sky. That's the last one. This one.
So what was the difference in that fraction of a percentage where you said it was different?
What's the difference between this and this?
Yeah. What What was the difference?
The difference between this and this is actually something that I can do in this class as an example. I can actually show you why this matters. Okay, and I want to see if I can do that because it's one of the tricks. So give me a second here to see if I can do this. Okay. So we saw that picture, right? Now, so that picture, notice this is that picture, but the picture is divided into two pieces. In this piece, this is the simulation. And this piece is the actual data. Okay? And if you look at this and this, wait, this it's not supposed to be this good. Hold on. Let's make it worse. That's supposed to be good. There you go. Okay, that made it worse. Okay, so this is the actual universe, and this is the simulation. Okay, and based upon this simulation, would you
What do you
say
mean simulation?
what?
What do you mean simulation?
I'm trying to make that picture look good. This is the real data. I want to match up the real data with simulated data based upon theory alone. Theory, mathematics, people with PhDs sitting down with computers making stuff work and not looking up, looking down at their machines. Okay? This is looking up at the sky, this is looking down at their machines. The idea is to make this match that. Yes?
Hoyle argued for a fixer, and what he said was there was a 1 in a billion or 1 in a trillion chance for this universe to exist at all.
Right.
Because all of the elements that you need to have this universe exist, each part of it is a 1 in a billion chance. of
Right.
existing.
Right.
So my point is, I have one.
Yes, if you have one.
The Big Bang, right, is something that is inexplicable to us, perhaps in absence of a fixer.
In the absence of a fixer.
Yeah.
Right. Yeah.
Higher power.
Right. 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 No. See. By the way, Howard has been in this class since the very first class, which is like 11 years ago. 11 years ago. So one of the things that I've discovered of Howard over the years, he tends to want a fixer, a prime mover. He likes prime movers. Okay. And as I said in the beginning of the class, there's nothing about the Big Bang that precludes a prime mover. Okay. Howard likes the prime mover. Okay. Because otherwise, without a prime mover, then you have to explain how come the universe is so juicy and perfect the way it is. And what I was saying earlier is you just invent an infinite number of universes that we happen to live in the lucky one. Okay, and you don't like that idea, no. And I like that one only because it gives me a way to eliminate a prime mover. I like eliminating a prime mover, so I like an infinite number of universes. They don't please me either. But that's my choice, one way or the
Maybe
other.
they also involve other prime movers.
Well, then you have a battle of the prime movers, which would be real fun. Or I think they have a movie. It's called The Avengers now, and so, you can see that. Yes.
It's almost like you have a stick of dynamite with a fuse on the end. Now, when you light that fuse, it finally gets to the stick of dynamite. I mean, one small stick of dynamite can make a hell of an explosion because the elements are there for the explosion.
Right.
So, I mean, just making a comparison to how the Big Bang came about.
Well, the problem is your problem is that there wasn't a stick of dynamite. That's
No, I know it's more than dynamite. It's
no.
other elements
So,
as well.
well, there's not even the Big Bang existed before there were elements. I mean, really, there's no good explanation for why did it decide to do that? Why didn't it just keep its own business and not become a universe? I mean, it surely had a choice of becoming a universe or not becoming a universe and chose to become a universe. I'm just going weird here. Yes.
I listened to a man do a video, and his question, he was a scientist, Lawrence Krauss, And he said, how did we get something from nothing? This is the big question.
Right.
Where did something come
Right.
from?
Where did something from? Yeah, I know.
So-
I'm not going to answer that question.
And other people have said,
How do
you
I-
know, between 50-50, there's 50% nothing, 50% something. Obviously, something wants something more than nothing.
What happens if I told you that when you add up all the universe, everything together, you get nothing? What happens if, would that work for you?
No, I heard him say that too. I mean, this stuff is empty.
No, I mean, we have dark energy, which is negative, okay? Negative energy, right? We have positive energy, we have negative energy. What happens if it worked out, and I'm not saying it did, but I'm saying it would be okay on some crazy level if you said something out of nothing and you don't like that, then why not just simply have the universe add up to nothing? The negatives add up to the positives, and you end up. And what happened is somehow or other the universe decided to separate itself into pluses and minuses that still would add up to nothing.
But excuse me, quantum.
Yeah, I know quantum stuff, but quantum stuff does that. But this isn't quantum. This is a universe. You can have something out of nothing, quantum, but it goes back to being nothing very quickly in an instant.
There is
The universe is going to become something forever.
The element that's permanent, according to some people, is consciousness. That we're creating with our consciousness, the universe.
Howard, I told you this before. I have spent 20 years going down that rabbit hole where consciousness creates the universe. Okay, it's an attractive place for me to play, but I've just put it aside for a bit because there are other theories that don't require my consciousness in order to explain the universe. Yes.
So is what Howard's saying that you could also go in the other direction and all of it could go back into nothing? Implode back in
Well,
instead of exploding.
Okay, that is another. Can the universe implode into nothing? Okay, and there is actually an answer to that thing, and the answer is no.
Why?
Because the answer is no because see what the people there was some people out there. They also got a Nobel Prize for having an accident. Okay, they said you know what, universe should be slowing down. Okay, because clearly there's gravity. Gravity pulls things back. You throw something up, it slows down and comes back. Same thing should be true of the universe. Sure, it exploded. I don't know why, but surely it's slowing down. Let me check out the rate at which it's slowing down. Makes a good idea. We got funding for it. Went out and checked it, and it was speeding up. And they got a Nobel Prize for it. And it turns out these days that, of course, it's speeding up. What were you thinking? Of course the universe is speeding up. Here are the equations. Okay, right here, the equations say that see, right over here, see the word dark energy right there on the screen? Dark energy. I'm going to be sliding these little sliders across the screen, okay? And I'm going to be trying to match this with that. And I'm going to be using just 3 little sliders because it's simplified here. And I'm going to try to invent the universe using 3 things. Well, these guys discovered dark energy, let's say 20 years ago. They discovered dark energy 20 years ago. And now it's become like, what were you thinking? Of course we need dark energy. You can't make a universe without it. If anybody hears a noise over there, I think they're spraying for cockroaches. Would you think that's what's going on?
Are they going to be spraying?
I don't know. I'll ask them. What are you guys doing?
The air conditioning.
They're not. They're fixing the air conditioning. Okay. Jumping to conclusions, I was. So really, what was crazy years ago and nobody had a clue becomes dogma today. Okay. Using the dogma of the 3 things. Okay, so the universe is made up of 3 things. It's made up of us, matter. I can feel me. Okay, dark matter, which I can't feel. In fact, it's invisible and nobody has a clue. And it seems to make up 5 times as much of the universe as we make up. What? The universe is made up of more dark matter than is made up of matter, and you can't see it. And the only clue you've got is to give it a name called dark matter. You could call it Charles's matter, any kind of matter. Could call it anything. They called it dark matter because that's all they know, and that to this day. They just know how much of it. Isn't that wonderful? And then there's dark energy, which a few years ago didn't exist, and now it turns out it makes up 75% of the entire universe. Again, dark energy. Don't know what it is? Know it's there for sure. Okay? So what I'm going to do is I'm going to invent a universe using those 3 things: dark energy, dark matter, and matter. And this is the universe I'm trying to make. You saw the picture. This is a little piece of it. This is the universe based upon what's here. And on the screen, what you see is matter at 20%, dark matter at 0, dark energy at 0. We will begin. I have the answers right here. I brought them with me because this little simulation doesn't tell you the answers until you find it. Okay? So I will know the answers. Meanwhile, I will just be fooling around, showing you things that aren't true. Yes?
Quick question. What did they discover or see, or what effect were there that made them say that there is something else that we call dark?
What is it that how did they know? What did they see? What did they know? That actually I'm not going to answer now, because that is really the subject of a much longer conversation. What they saw, though, in the short thing is dark energy. They saw the universe was expanding faster and faster. That's the answer to the dark energy question. That's a 75% question.
So the things that were visible.
These things are visible like crazy. The effects are visible.
There has to be something else.
If the universe is accelerating in its expansion, dark energy. If the universe, if the stars seem to be going around in paths that are not explained by the matter that's in the galaxies, if the galaxies can't be explained by the gravity of the stars that we see, if we need to postulate there's something more going on in those galaxies than are in the galaxies that we can see, that we postulate things we can't see. We call it dark matter,
It's
and
dark
then
to us. It doesn't mean that the matter dark.
no, it's dark.
Us.
Dark to every it's us. When you say us,
Us human beings who are doing all
no. You are missing a point when you say us. Okay, us. You have your eyes. Okay, you have your eyes. That's us. Turns out astronomers have a different set of eyes. They have an entire electromagnetic spectrum that is also us, okay? And that's everything. And in the last few years, they've added to us gravitational. So now we can see things with gravitational telescopes and electromagnetic telescopes. What is it you think we're missing? We're not missing anything. Us is all the instruments.
They just expanded
All
the
the-
spectrum, but who knows how much more spectrum there is that they don't have
Okay,
yet. I mean,
so you've invented parts of the spectrum that we still haven't examined. Well, I will grant you that there are parts of the spectrum that haven't been examined because it goes infinitely in this direction and infinitely in this direction. And if we've only measured a ridiculous amount in this direction and a ridiculous amount in this direction, and you say that maybe that's not enough and there's more that yet to be measured, I agree. Nevertheless, I think that what it's dark is dark. What we are looking to find out what the stuff is. Every day there are people buried in the bottom of mines, flying in space, looking for this stuff. Every day they're looking. They're not wasting a minute. Okay, they just haven't found anything. So until they find something, it's dark. After that, they'll give it a name. Right? Okay. So let's invent the universe. We have 3 sliders. Okay. We have data. We have experimental stuff, and the data that we have is determined by this last satellite. And this last satellite has a resolution of about this big. In other words, it can't see stuff that's much smaller than this 1 degree. So the next satellite we build will be able to see smaller things than that. And believe me, after they find smaller things, they'll have more to say. And it could be different, but probably similar. Yes.
If the size of the Big Bang originally was the size of an atom, let's say,
Yeah, and even smaller.
and even smaller, how could something so small have all the elements in it, including the gases that make up the stars and the universe and everything, explode in such a manner to create a universe?
Okay. You're asking me,
I mean,
you're saying this is
what I'm saying is there an argument for astronomers that would say they're against the Big Bang theory?
there isn't anybody who's against the Big Bang. Okay. There really isn't. The Big Bang is the Big Bang. Now there are plenty of things that you can nuance about the Big Bang. You could nuance the hell out of it. You could probably nuance the hell out of what you just said. You could say, you know what? First second of the Big Bang, I don't like it. I think we should come up with another theory of the Big Bang that involves clowns. Okay, at that point, clowns were around for the first second. They did a lot of stuff, and then we see the rest of the universe. Okay, but before that, I can't believe it was anything but clowns. Okay, because really, I'm telling you that we have a theory that doesn't involve clowns. Okay, that's quite cogent and goes back, obviously not to t equals 0. You know why you can't go back to t equals 0? Because you have to divide time by tens. Okay, the first tenth of a second, the first hundredth of a second, the first thousandth of a second. Exactly when do you get to 0? Never. Okay, so they only have answers that go back to maybe the first 1 to the 10th to the 47th of a second. They don't have an answer that goes back before that. So if you want to go back to t equals 0, nobody's there at t equals 0. People are still saying, well, there is a point that we just don't know. But that's ridiculously close to t equals 0. But still, there's a lot of time between 10 to the minus 47th and 0 and 1 second for clowns to be there doing something else besides what we think is going on. Let me do the slider. Okay? I love this Big Bang theory because I'm believing in it now, you see? I'm increasingly believing in something that's been very hard for me to buy because I didn't know enough. The more I prepare for this class, the more I know, the more I buy. So, let's look at that graph. And one more thing about this graph. The red indicates hot, the blue indicates cool. Okay? The temperature of everything is 3 degrees above absolute 0. It's everywhere is 3 degrees above absolute 0, everywhere here. The difference is this is 3.000001, and the other one is 2.99999. And so the 2.99999 is blue, and the 3.00001 is red. Okay, very small differences in temperature. Nevertheless, that's what we're playing with. It's real. They actually measure these differences. So I will move up. Let's move matter up to 100%. Okay, that does not look like the actual picture in the upper right-hand corner. Okay, the universe is not made up of 100% matter. Okay, let's put it down. Let's say at 50% just for fun. Still not good, but let's throw in some dark matter to make up the other 100%. So now we have 100%. 50-50 still doesn't look good because the thing in the upper right-hand corner is still not good enough. I want to change the camera a little bit. Okay. Okay. Well, let's reduce these. Let's add in some dark energy. Okay. And that doesn't seem to help anything either. Well, what happens if we reduce the amount of matter in the universe? Okay, we'll pull that down. Well, not so much, but it seems to be better. What about if we reduce the dark matter a little bit. But that seems to get closer. Okay, what about, oh, and notice there's one other thing that's going on here. As I change all of these things, we get three numbers here. First of all, the age of the universe keeps changing. Now it's at 11.1 billion years. The correct answer, if you are cheating at home, is 13.8. So you want to look at this number to see if I get to 13.8. Okay? Also, another number you want to look at is the similarity with our own universe is a number over here, and right now I'm at 55% similarity with our actual universe. Yes?
You said it was all a fraction of the difference. Was it hotter at the moment of the Big Bang and getting cooler?
Yes.
Or
Yeah, it was hotter.
Is it getting cooler? Is it getting
It's
hotter?
always been getting cooler. The Big Bang, it's going to be cooling off forever. That'll continue. It's cooling off.
So we're expanding and cooling off.
Yeah, just like you'd expect anything when it expands, it cools off. That much is true.
Also, will there always be this buzz that comes from?
The buzz will always be there. The buzz will get dimmer, cooler. So that we're at 55% with 1.1 billion years old. Okay, I'm going to now let's say increase the dark matter, and you can see that that's not working out so way. It's going down to 50% in 10.5 billion years. So better decrease the dark matter back lower. Oh, bringing it back lower seems to give me a better number. 58% similarity. Maybe you can't tell from looking at the picture, but maybe you can tell by looking at the 56% similarity. Okay, what about the dark energy? Let's bring up the dark energy and see if that makes a difference. Oh, 57%. Okay, 58%. We're doing well. 58%. We don't seem to get better. Maybe there's too much matter in the universe. Let me lower the amount of matter in the universe. 59%. We're doing better. Okay, 62%. We're cooking. 63%. Really cooking. Okay, 71%. We're getting better and better, matching the theoretical computation with the actual picture of the universe. You can't really tell by looking at the picture by now. It looks to you, you can't distinguish one from the other. But the computer can, so you got to trust the computer. I'm bringing it down now, 75%, 76%, 80% the same, okay? 84%, that's good, okay? I'm going to leave it at about 5% where I know the answer is. We're at 96% similarity. I'm now going to increase the dark matter a little bit more to where I know the answer is, and increase the dark energy and decrease the dark matter, or increase the dark matter. And there we go, 99%. That's close enough. And I have matched the universe. I'm at 14 billion years. It's 99% similar. And this is the universe. Normal matter, 5%. Dark matter, 27%. And dark energy, 72%. Those numbers are close to the actual numbers. I could move the slider and I'd get 100%. That's how we know that those are the numbers, because this is the method that we use to tell what the percentages are. Nothing else matches it. You have to believe a little bit in the fact that these scientists have been to school and you haven't. Okay, so that they know what they're talking about. And I have been studying what they talk about for a while, not at the level, of course, which they talk about it, but I'm a believer now. Okay, now we'll continue next time to talk about the Big Bang. We still haven't gotten to the controversy that began all this conversation. There is something wrong with this theory. This, they discovered, doesn't agree with another observation that they've made. And that other observation tells you a different answer for the age of the universe than and the percentages of things. So we have, if you will, an argument in the world of astronomy. And that's a good thing, because first of all, people get to get PhDs, okay? I mean, that is important. There'll be hundreds of PhDs coming out of the fact that there's something we don't understand, okay? So I'm just going to come and explain to you again next week. Yes?
Let me just ask, sometimes it says closed universe, sometimes it says open universe.
Uh-huh.
What is the meaning
That's very good.
When you get to that, it's close, but when it was.
Yeah. When you get to the right answer, let's get to the right answer and see what it says. When you get to the right answer, the right answer is that and
Flat universe.
that's the right answer. The right answer is it's a flat universe. Okay, so
Flatter?
flat,
Flat.
flat.
That's what they used to believe.
Yeah, the universe is flat.
Somebody's got
Okay,
it in.
now
In the Middle Ages?
so try to imagine.
So is.
The reason why the word flat is you ask the question, what is space expanding into, and it isn't expanding into anything, but try to imagine that space is, instead of three-dimensional as we expect it to be, try to imagine that it's two-dimensional, so we can try to understand its shape in a three-dimensional space. Okay, so space is two-dimensional and exists in a three-dimensional space. But space is three-dimensional, so does it exist in a four-dimensional space? Okay, no, it doesn't. We're just doing an analogy here.
See, this is the thing, everything we're thinking matches us. I mean, human beings live in a two-dimensional space, in a three-dimensional space, and that's all they know. So suddenly, the universe is
Right.
two-dimensional.
But I'm gonna talk about the word flat, and this should bend your mind, because for one split second we're going to imagine a fourth dimension that doesn't really exist. It just mathematically exists. Not scientists are capable of thinking in math with n dimensions, and they don't have any problem with it. We're going to expand three-dimensional space into four dimensions by analogy, but we're going to use two-dimensional space, and we're going to use that to imagine what flat means. Okay, so if the universe is flat, what does that mean? It's flat.
Can't even imagine.
No, you can't. It's flat. It means flat. That's what it works. They use the word flat. It means flat. Flat. Okay? Now, flat is flat. Now, when it's not flat, it's curved, right? Okay? This would be open, in the sense it goes on forever, but this would be closed. Okay? Okay, so so when we saw the word closed before, we saw it like this, not flat. Open, closed, open, closed. That's what they mean by those words. They are mathematical terms. But in order to bring you along in the conversation, I've given you a graphical analogy. There is no fourth dimension. There's just like when Einstein tells you that space is curved. What does he mean? Okay, curved how? Well, it makes sense. You pass that along. You answer that question. So that's all it means. The universe is flat. It's 13.8 billion years old, and we've matched it 100% to the data. Yes.
Is that what the three dimensions are you just showed us on the paper? Flat, curved, and
Yeah, but this would be this is curving through the fourth dimension.
Oh, it goes to the fourth dimension.
Right, so
there is no fourth dimension.
There is no fourth. It's a mathematical construct. Okay, so in order for you to understand what curved space-time, and by the way, the word is space-time, not space. So what curved space-time is like, you'd have to Google curved space-time, and you'd find out some stuff. Okay, and then you try to understand that. And I try to avoid it. Yes.
If we look at our galaxy, it's flat, essentially.
Our galaxy is flat is a flat galaxy in three-dimensional space. It has nothing to do with this conversation. Galaxy is flat. That doesn't mean space is flat. Space is a three-dimensional space, and we call it flat. Okay, we would call this room flat. Three-dimensionally, it's flat. That's what does that mean? It means this way and this way is not any different from this way and that way. You take out your ruler, it doesn't change. Your ruler doesn't change as you start measuring in different directions. Your ruler is good no matter which way you measure it. That's called flat. If the universe was not, it was curved, your ruler would change its shape as you measured this way or that way. That's curved. It would be as if there's a stretchy in that direction and a compression in that direction. Okay? So anyway, next week we will be here. And apparently we'll be talking about the same thing over and over and over again, all right? Until finally somebody gets it, or me, one of us, okay? So, see you next
Have
week.
you seen